Hi there, it's Dr. Fox here again on these series of lessons for A-level AQA physics. This is the Simple Harmonic unit. This is the third lesson of three, so go and look at the other ones. If you've skipped ahead because I mentioned about resonance and forced and free oscillations, then this is a good place to be. It's not going to be a long lesson, but some of the concepts around here are definitely A-level physics. They're not straightforward. And there's some great videos out there on YouTube explaining these things in lovely animations. But nevertheless, the concepts are the same. And if you can imagine a swing with a child on it, and you being the father or the mother pushing it, then you can pretty much work out what forced and free oscillations are and damping. And so if you've got an imagination, I should think you'll be able to cope with this reasonably well. The only other thing I'm going to tack on here is a variation of kinetic energy and potential energy. Well, that's what these mean. And the total energy with both displacement and time. So I'm going to have a look at those. And we've looked a little bit at that in lesson one. But we'll look at it again. So qualitative treatment of free and forced vibrations, resonance, effective damping, sharpness of resonance, and I'll show you what sharpness of resonance is, and examples of these effects in mechanical systems in situations involved in stationary waves. Stationary waves is back in AS, of course, and that's stationary waves on a string, or in stationary waves within pipes, because of when you like the bottle effect. I haven't seen any questions to do with these in exams for all the A-level it's been doing, so I'm going to take some guesses on what that could be. But child on a swing is usually quite good. The idea of forced and free vibrations, and some musical instruments as well. And then, of course, investigation of the factors that determine resonant frequency of a driven system. If your teacher's got enough time to do that, then well done. You must be in a school that's got tons and tons of time. I don't think I've short of blowing across the top of a bottle and taking everybody out to go on a swing, then I can't see a lot of teachers spending a lot of time doing that. Okay, so get your notes out. Question is energy, resonance, and damping. These are good ones to write down. Kinetic energy and potential energy, free and forced vibrations, resonance, and some examples where oscillations are damped as well. So that's worth writing down in your notes. The diagrams around here I'm going to come to in more detail. But just pause the video and get those down. It's important to write down these terms so you're used to writing down free and forced vibrations. So in your notes you can look back. What's a free vibration? What's a forced vibration? And what is resonance? And there's the definition of resonance within there. That's why you need those. And be comfortable with writing those and be able to deliver them when somebody asks you what resonance is. Okay, once you've got that written down, after you've paused this, I'll move on. So here we are. Here's kinetic energy and potential energy. So we've got energy up the side here. And let's say this is an energy in a pendulum system. You've got the total energy in here. You've got Ke plus P. Now Ke is this blue line. P is this blue line here. K is the dotted line. So maximum potential energy is when you pull the pendulum off to one side and going to release it, because that's your potential energy. Once you've released it, of course, it'll swing down. It gets to the bottom, and it's going its maximum velocity where it's going through zero displacement. That is at this position here. In other words, your potential energy is a minimum, and your kinetic energy is a maximum. And of course, as soon as it goes through it, it goes up to the other side. It will stop momentarily, and there you'll end up here, which is your maximum potential energy and your minimum kinetic energy, exactly halfway through. And then, of course, the whole thing will come back again, pass through maximum kinetic energy, minimum potential energy, and then go up to the end, where you end up right back at the beginning with maximum potential energy. And remember, this is one period. And note, it looks like you've got two waves in here. And this is why kinetic energy and potential energy are different to your displacement, velocity, and acceleration graphs. You effectively got double in there. And the reason is this whole thing stays positive. Your energies here are somewhere. Your potential energy is positive, your kinetic energy is positive, and they're interchanging between them. If you go back to lesson one, I showed you how these vary with them. And there's a really good exam question which demonstrates this, which is an object oscillating simple harmonic motion as a time period t. The first graphs show how its displacement varies with time. Which of the subsequent graphs, A to D, show how the kinetic energy, Ek, of the object varies with time? So this is your displacement graph, and you can see it's got this period here. And this is at time t in particular. But maximum displacement, zero displacement, maximum negative displacement, zero displacement. So when we're talking about the kinetic energy, we're interested in the velocity. So where is velocity the maximum in a simple harmonic motion? Now, maximum displacement, of course, is when it's come off to one side. If it's at maximum displacement, its velocity will be zero. If its velocity is zero, its kinetic energy will be zero. So we're already looking for something where at maximum displacement, the velocity has got to be zero. Let's look down here. Nope, nope, zero, just above. So it can't be any of these two. So it's got to be, well, it's looking like this one, but let's carry on. Okay, so at zero displacement, you've got maximum velocity. So let's carry on. So at zero displacement, you've got, these two are both maximum. Right, okay, we'll see. Oh, hang on. But here we are, look, we've got two of these waves in here. We've only got a single one in here. That doesn't make sense. So let's go back to our thing here. So this has got to be this one. So maximum displacement, zero velocity, therefore zero kinetic energy. It's not zero here, it can't be that one. So if I carry on here, so if we've got zero displacement there, it's got to be that one then, hasn't it? Because look, zero displacement is when we've got maximum velocity. We've got maximum velocity again. It can't be that one because it's got zero. So it has to be C. That is a great question. I can imagine that being asked with potential energy, for instance, as well, or even a combination of the two. And remember, your total energy of the system remains constant. Because if you look at the previous slide, if we add up potential energy and kinetic energy, we always have exactly the same energy, which is equal to the maximum of either of them. So you end up with a straight line. You can see that being a multiple choice question. So there we go. Applied force. So free and force vibrations. Here, I got the same t-shirt as that chap. So if you have tuning forks, which you may not have come across in your life, but basically they're small pieces of metal which you hit them against the table, they go woo, and they will resonate at a certain value. They're called tuning forks because they're used to tune instruments, particularly pianos, because they will always resonate at a certain. Resonate means vibrate. So if you just leave them, if you hit them, they will vibrate, and the length of the prong will determine how much they vibrate. And what's a really weird experiment, which your teacher could do, is if you hit a tuning fork over here, and you have an identical tuning fork at a distance, it will also start to vibrate. Why? As you can see here, the pulses of the air that go in push the prongs in and then out at exactly the right frequency. And this is called resonant frequency, and then it's called the free vibration. But then we're forcing vibrations into this one here. Now this is where the force vibration matches the free vibration, we get something called resonance. So resonance is when you have a system where the force vibrations, so in other words, what the force you're putting in to set the simple harmonic motion going, matches it. Now, of course, if you match it, the amplitude will become very, very large indeed. And this is quite a creepy experiment. You hit it and go, and then you'll all of a sudden hear this other one just start going, almost like because nobody's touching it, it starts to do it. Then you put your hand around that one, and that one will carry on going. Really good experiment. Very quiet, but it's very good. And of course, another one is where you have something called force vibrations on here. This will start to resonate, but it requires an input force all the time. So if you have a bottle that's half full of water, you've done this with a bottle, and you blow across the top, you'll get a noise within there depending on the level of liquid between. And somebody's done the experiment, by the way, about the square root of the volume inside bottles. But this is not the A level. This is where you're forcing air across the top and you're forcing a vibration. And it will start up with the natural frequency, but the moment you stop, it will decrease. The damping is huge. So that means damping means that basically the oscillation is getting less and less by some external force. And so therefore you're inducing resonance within it, but it's not the same as the top one because you're not continuing to put that force in. And it will stop fairly quickly, depending on if you stop blowing, therefore it will stop going. So there's your example. So if your tuning fork has resonance because you hit it and it just goes to its natural frequency, but you can cause it in other things, just like it's in this tuning fork here. You can cause resonance in others by matching your driving frequency, your driving force frequency, to be able to do it here. And there's some great videos on YouTube. Go and have a look. This is Galloping Gertie, of course, which is the famous Tacoma Narrows Bridge, where the wind that was going across the bridge happen to match the natural frequency of the oscillations of the bridge, and the velocity of that wind was as such that it just carried on going and it actually destroyed the bridge entirely. And that's a forced vibration that matches the resonant frequency of that. So if you match your resonant frequency with a forced vibration, you get very large amplitudes. In this case, it destroyed the bridge entirely. Go and have a look at it. And just to rewind, this T here is your natural frequency. So if I let it go, therefore that will be it. Now, if I match that period with a force that gives a force at exactly the same period, then you will be getting very large amplitudes indeed. And that's what can set up and increase amplitudes of simple harmonic motion. And the easiest way to imagine this is a swing. So we have free vibrations and forced vibrations in musical instruments, but just think about swing for a second. You sit your child on a swing, give them a push. Now that push will immediately set up the natural frequency of the swing rather. So they'll just go backwards and forwards. And eventually that will swing to a stop. Why? Because it's damped. It's damped because of the friction at the top of the joint of the swing, and also because the air resistance within it, and your child might be scraping the feet along the floor. However, if you match your force vibration to the resonant frequency, i.e. you push at exactly the same frequency as the swing, in other words, you're pushing them at the one end, you're matching the natural frequency because you push at exactly the same time period as the swing. And if you keep pushing, of course, the amplitude will get greater and greater and greater, and you will have very large amplitudes at resonance. If you stop, of course, that will eventually swing down, and that's where you end up with this graph here. As soon as it's taken away, of course, you end up with this damping. If you have a strong periodic force, which is matching to it, then you end up with very, very large frequencies. Force vibrations, that's what you can get it set up, but if it's not, so the strong periodic force, which is different to the natural frequency of the body, you end up with much smaller amplitudes. So you can do it, but it means that it's going to keep going in much smaller amplitudes, and it won't have a natural frequency afterwards. So you can get things going with force vibrations, but it will not be at very large amplitudes. Incidentally, if it's a multiple of frequency, so imagine I'm pushing here, and then I push once when my child is at the other end, and then I push again when my child is pushing towards me, I will then, of course, produce large amplitudes because I'm a multiple of the frequency. So I haven't seen their question about that, but you can imagine that happening. So in other words, if it's, for instance, a time period of 2 seconds to go there and back, if I'm pushing a period of 1 second, you will get the same large amplitudes. If I'm pushing at the amplitude time period of 4 seconds, i.e. every other swing, I'll increase the amplitude, but not by a great deal. Okay, so you can see how those differences can come through. So free vibrations is when there's nothing happened whatsoever. It's just an initial force and then it just carries on. Force vibrations, you can either get very large force vibrations if you match the resonant frequency, but it's different. If the periodic force is different to the resonance, you're not going to get that larger amplitude, unless, of course, you have a multiple of the time period, or multiple of the frequency. Okay, so damping can be brought on in a number of ways. If this is a mass spring system, you can see you just put a big card around it, and that produces air resistance, so therefore we've got damping. In this case, you can put a little paddle inside a liquid that's hanging beneath it, and that will cause viscous damping. So the damping will cause that to go much slower, and therefore you end up with simple harmonic motion that looks like this. Instead of those nice even graphs that we've seen before, we end up with damping. I put light damping here. Basically, light damping is when you get quite a lot of, you get multiples of it happening, and it will carry on going on. Heavy damping is, of course, when it probably doesn't even make one. And then a good example of heavy damping is the suspension system on a car. Poor suspension is when it's allowed to go into its resonance, but of course it's damped so much by oil means. So basically, if you put oil in something, so it makes sure it just doesn't even do one. So you get heavy damping, which probably just go up and down and stop there. Whereas light damping is when you end up with multiple periods. Okay, So this graph I'm going to dwell on for a minute because it tells you a lot. So for instance, each one of these lines here represent the amplitude if I have a driving frequency at this angular frequency, this periodic force. So the driving periodic force has an angular frequency. Now, the angular frequency here, natural angular frequency of the system, is omega 0. So I can, if I halve my periodic frequency, so this is now the resonant frequency divided by, resonant angular frequency, my apologies, divided by 2, you end up with very small amplitudes. If I then make it 3 halves, I get very small amplitudes there, but if I match it, I get a reasonable amplitude. Now introduce damping to that situation. If I end up with heavy damping, my amplitude is very low. Makes sense. If I have medium damping, high, and it's much more sharp. Now this is the idea of sharpness of resonance. I have a very sharp resonance here. If I have very small damping and I'm matching my periodic force with the resonant frequency of this. So T equals 2 pi root m over k, or L over g, if you've got a spring system or a pendulum system. And you can imagine damping in pendulum systems, probably the size of it, or maybe it's going through water or something like that. But if my periodic driving force is matching that resonant frequency, even with heavy damping, I will get some amplitude because the heavy damping is enough. If I stop the periodic force, of course, this will just go to 0. But of course, if I've got very low damping and I'm matching the frequency, then I get a very sharp, tall amplitude because my periodic force is matching the resonant frequency. So there's 2 things to consider: the resonant frequency and the period of the driving force, of the periodic force. If those 2 match, you get very, very high amplitudes, but only if there is small damping. If they're matched and it's heavy damping, you get a very low amplitude. If your periodic force does not match, so it's either half or 3 halves, then of course your amplitude is going to be a lot lower in this case. So that means that you end up with lower amplitudes. Just like I said before, if you're pushing when there's nobody there, that force isn't going to do anything. But if you're matching it, yeah, okay, you're getting it, but it's going to be nowhere near as much amplitude as exactly the same periodic force. So that is a diagram that has popped up in exams, and I'll show you an example of that in a second. And the amplitude increases with lower amounts of damping. Makes sense. Okay, worth dwelling on that graph because it's telling you a lot. And here we are. This is an exam question, multiple choice again. Oscillatory system, basically simple harmonic motion, subject to damping. Something's happening to it to make sure that it's going to not be swinging freely or bouncing freely. Is set into vibration by a periodic driving force of frequency f. The graphs A to D show, which are the same scale, show how the amplitude of vibration A of the system might vary with f for various degrees of damping. Which graph shows the lightest damping? So you've got to think back to the graph I just showed you. Which is the one? We're going to have a sharp resonance because if it is at the periodic driving force, if that periodic driving force matches it, there's going to be a sharpness somewhere in there. If it's light damping, therefore it's going to be something sharp. So these 2 are the only 2 that are sharp in there. But which one is it? Which one matched the other one? It's got to be this one. This is heavy damping, of course, and this is here. And in this case, of course, this must be the natural frequency of the oscillating system. So it's going to be B. Okay, that's it. So simple harmonic motion in 3 lessons. Qualitative treatment of free and false vibrations. Just think of the swings. Free vibration is a swing just going on its own. False vibrations are when you're pushing the child and you're going to get larger amplitudes. Resonance and effect on damping and sharpness, and of course examples. We're finished. Okay, let's move on.